I've got two equivalent formulas for a function up here on the board. Y is sine of 2x minus pi over 2. And here I'm just observing that if I wanted to factor out that 2, that's equivalent to 2 times the quantity x minus pi over 4. Now, either way, I can see I'm doing two things to x before I plug into sine. I'm multiplying by 2 and I'm subtracting a number. It's just a question of the order in which I do things. Okay? Here I subtract first and then multiply by 2. Here I multiply by 2 first and then subtract. Okay. Now, that's going to correspond to transformations. I'm going to be shifting things, that's from the subtraction, and I'm going to be shrinking by a factor of 1/2. That's accomplished by the multiplying by 2. Remembering that horizontal transformations are counterintuitive. Here, I subtract first and multiply by 2 second. I do the transformations in the opposite order. So here I would shrink and then shift. Here, I would shift and then shrink. It's for that reason that I prefer this version. Because pi over 4, when I've actually graphed things, I'm going to be able to look at it and say, oh yeah, I shifted things to the right, pi over 4. I'm going to be able to see that number there. Here, I would shift pi over 2 to the right, but then I would shrink everything. And that essentially shrinks the amount that I've shifted things, so I'm going to end up shifting things pi over 4. I like to be able to see that number, so I'm almost always going to rewrite things this way. The book almost always gives you things in this form. It doesn't matter because they're equivalent, okay? And I'm going to show you a way of dealing with these that's going to allow us to do both of those transformations at once. I just kind of like this version because I've got a visual check. At the end, I should be able to look and see, did I actually shift things pi over 4 to the right? Okay. All right, now if I were going to do this the traditional way, I would list that I'm going to evaluate things and then the corresponding transformations. So I'd say the first thing I'm doing is subtracting pi over 4, then I multiply by 2, then I plug into sine, which is my parent function. Since I'm doing these things before the parent, they're both horizontal changes, and the rule is we move away from the parent function, which has me doing the transformations in the opposite order in which I evaluated things. So multiplying by 2, that was shrinking by a factor of 1/2. Subtracting pi over 4 shifts things pi over 4 to the right. Okay, excellent. Now, we know how to do transformations one at a time. So I could certainly start with the sine graph, shrink it by a factor of 1/2, shift it pi over 4 to the right. Not a problem. We know how to do that. But there's a nice shortcut that applies for periodic functions. Now, the parent functions that we had previously, x squared, square root of x, even when we added exponentials and logs, none of those were periodic. None of those had a pattern that repeated itself. All of our trig functions are periodic. So this shortcut applies to all of them. So let me just show you how that works. Essentially, I know I'm taking sine of this thing. Well, I know that the period of the sine graph prior to any transformations is 2 pi. And what that means is that sine does its thing once over the interval from 0 to 2 pi. So this function is going to do its thing once. As the input to sine, that 2 times x minus pi over 4 varies from 0 to 2 pi. Whatever my input is, put that in between the starting and ending point for my usual period that I choose to draw of the sine graph. And now I'm just going to take this inequality and solve it for x. Okay. So the first thing I would do is divide both sides by 2. So I get 0 less than or equal to x minus pi over 4 less than or equal to pi. Okay. That gives me a new starting and ending point, and that would be the starting and ending point for if I was just doing the shrinking. We did that a couple videos ago, and we saw that we started at 0 and we ended at pi for the one period, full period that we drew, and then it went on forever and ever repeating that pattern. Okay. Now to solve for x, to do the other transformation, I'm going to add pi over 4. So 0 plus pi over 4 is pi over 4. Here in the middle, the pi over 4's cancel, so I get x. And here, I need a common denominator. So that pi was pi over 1, multiplied by 1 in the form of 4/4, so we've got 4 pi over 4. We're adding pi over 4. We're going to get 5 pi over 4. So, we've got a new starting point of pi over 4 and a new ending point of 5 pi over 4. Now at this point, I usually like to do a quick double check. I'm going to just calculate my new period. And I have two ways of doing that. One we talked about before we were doing any of the shifts, when we were just looking at stretches and shrinks. We said take a look at the number that you're multiplying by. Take the original period of 2 pi and divide by the absolute value of that. I'm still going to do that because the shift, that doesn't affect the period. That takes something of this length and it just moves it to a different location, but it doesn't stretch or shrink. It's the multiplication that does that. So I can say that the new period is 2 pi divided by the absolute value of 2. Of course, that's 2 pi divided by 2, which is just pi. So that should be the new period. But the period is supposed to be the length of the interval over which this function does its thing. I could calculate that by taking my ending point and subtracting my starting point. That would be 4 pi over 4, which is pi. It checks. It's a quick check to make sure that you haven't made a careless mistake here. You've got two ways of calculating the period, ending point minus starting point, or original period of 2 pi divided by the absolute value of whatever number you were multiplying by x. Okay, excellent. So I sort of now know when I'm graphing this, I'm going to be concerned with the interval from pi over 4 to 5 pi over 4 because that's my starting point. Okay. We think about graphs of sines and cosines. We're always plotting 5 important points. And those 5 important points divide the graph up into 4 intervals. Prior to any transformations, those intervals correspond to the quadrants, from 0 to pi over 2, from pi over 2 to pi, etc., etc. So I'm just going to call that my increment. So the new increment, I'm going to take that new period and I'm going to divide it into 4 equal pieces. So then I can say, what are the x values that I care about? Well, I know, because we just calculated it, that I'm supposed to start at pi over 4. Now that happens to be my new increment, but this was my starting value that I found. So that's why I'm starting at pi over 4. But I'm going to get my next x values by just adding a quarter of the period. So my next x value would be pi over 4 plus pi over 4. That would be 2 pi over 4. Then add pi over 4, I'd get 3 pi over 4. Add pi over 4, I'd get 4 pi over 4. Add pi over 4, I'd get 5 pi over 4. Kind of nice, that's supposed to be my ending value. I added my increment 1, 2, 3, 4 times, and that gives me my ending value. So again, there's a built-in double check right there. Okay. Now, of course, some of these can be reduced. So what I'm going to do is when I mark those off on the x-axis, I'm going to go ahead and give the reduced versions. Okay. So I'm starting at pi over 4. Now, do be careful. As soon as I indicate that that's pi over 4, I have indicated that this distance is pi over 4. I need to respect that for the rest of things. So how does that relate to my increment? It happens to be my increment. So as I'm counting over, I'm going to be counting over by that same distance. So my next point, 2 pi over 4, reduces to pi over 2. My next point, 3 pi over 4, doesn't reduce. 4 pi over 4 reduces to pi. And then my ending point was 5 pi over 4. Now, we haven't done any vertical transformations, so we've still got a high of 1 and a low of -1. And this was a sine function, so that starts at the middle value. So this was my starting point. So we start middle, high, middle, low, middle. So I can connect those dots, and I want to make sure I include an arrow to indicate that it goes on. Now I do need to be careful over here on the left side of the graph, because if I'm looking over here, okay, if I'm not careful, I'm going to just go something like that, and I've just said that the y-intercept is right there. Now the y-intercept is often a very important point. So I want to be careful. If I'm going to cross the y-axis, I want to make sure I cross it at the right point. So either don't go that far, just sort of have your arrow to indicate that we keep going, or observe, hey, that's one increment, so I'm going to be at a low value here. So I can actually see exactly what my y-intercept is. But be careful that you're not careless about where you cross the y-axis, because people reading your graphs are often going to say, oh, important points, x-intercepts, y-intercepts, highs and lows. Okay, so you want to make sure that if you cross the y-axis, you cross it at the right place or about the right place. If you're not crossing at a high, middle, or low value, you're going to be estimating where you cross, but you should be able to do that by just making sure that you preserve the correct scale along the x-axis. Okay, excellent. We'll try another one of these in the next video. I think we'll do one more together, and then we'll start mixing it in with some vertical stuff.